It's really my privilege and my honor, as well as my pleasure, to introduce our speaker today, Professor George Kaniadakis from Brown University. Now, in a way, George doesn't need an introduction. One can safely say that he's one of the world's preeminent applied mathematicians and computational scientists, with many pioneering contributions over the years. So, but very quickly, George received his PhD from MIT in 1987. He was a faculty member at Princeton University before he moved to Brown University in 1993, where he is the John Palmer Bear Stowe Professor and the Charles Pitts Professor. He's also affiliated with MIT, where he's a research scientist, and with the Pacific Northwestern National Labs, where he heads a big group, and he heads many different groups, as you can see from his slides. Now, as I said, he has many seminal contributions in various areas of computational science and discontinuous Galerkin methods, spectral element methods, generalized polynomial chaos, fractional PDEs, microfluidics, nanofluidics, and more recently in machine learning, and really pioneering a very important part of machine learning that he's going to talk about, PINs and its applications in scientific computing. George he's a member of a fellow of all professional societies that you can think of: SIAM, ASME, AIAA. He has received many awards and honors. The list is too long, but let me mention the Ralph Kleinman Prize from SIAM in 2015, among others. So George, it's really our pleasure to host you. And maybe one, just to testifying your impact, is the fact that you have an H-index which is more than 100 now, which is really remarkable. So your impact on applied mathematics is massive, and we're truly delighted to have you here, and we're looking forward to your talk. The floor is yours, George.
Thank you very much, Sid. That's very generous of you. And can you hear me?
Yeah, very well, very well.
Okay. That's great. I just invested on this new blue technology for for a microphone. That's good. So I want to talk about computational solutions of partial differential equations and using neural networks. Kind of different take on what you may have heard so far, because I want to talk about not just function approximation, but functional approximation and operators approximation. And just so that I give you the main theme from the very beginning, what you saw in this movie that I played before. Let me see if I can play it again. Let me see if I can play this one. Anyway, what you see here is some data which some of my friends from Germany, LaVision, gave me. And I drink coffee every morning. I just had my coffee. I was very curious to see what is the maximum velocity over my espresso cup, and can I quantify the pressure field and the velocity field everywhere, given that they give me a temperature. So that's like something that I'm curious, and I have some data, but obviously it's an ill-posed problem. So the main theme of my today's talk is, can we solve problems using PDEs, which we cannot solve easily with conventional methods? Okay, so that's why I'll get back to the coffee later on, but let me, by the way of introduction and outline, give you some glossary that I will be using today. PIN is a physics-informed neural network I will talk about this in the context of function approximation. DeepFNet is a functional approximation. I will give you some application and what kind of networks would approximate the functional, very useful for autonomy and other big applications, important applications. Then my favorite one is DeepONet. It's a paper that will appear in Nature Machine Intelligence soon, and it has 16 different applications. And it's basically neural network at the level of operator, of system identification, a nonlinear operator. And then how you can use, if I have time, if I don't run out of time, I will talk about DeepMNM, this sweet new framework we introduced, how you can use DeepONets as building blocks to solve multiphysics and multi-scale problems very, very fast, maybe 10,000 to 100,000 times faster than the state of the art. And that's our current project with DARPA And we have to produce results every week with this project, but so I'm very excited about it. So just to get us started, universal function approximation first was developed by George Saipengo when he was assistant professor here at, not far from where I live in Boston at Tufts University. He proposed if the function is a continuous function, then a single hidden layer with a activation function sigma, which is non-polynomial, will be a sigmoidal at the time. That's what they said. Of course, we know now this activation function could be some other nonlinear, non-polynomial function, but a single layer is enough to approximate this at the this function at the arbitrary accuracy. This is sort of the basis of almost everything. The subsequent work by Maskar, one of my collaborators, currently my new project on NURI that we are kicking off tomorrow. Actually, this a new NURI, if you want to watch out, is a multi-university collaboration between myself, Brown, and Caltech and Stanford, University of Utah, on machine learning for PDEs, which is the topic of my talk today. So how about discontinuous functions? This theory also covers discontinuous functions, but shallow networks do not work very well, but deep networks work very expressive and work really well for discontinuous functions. And I want to demonstrate that with something new that we have. One of my collaborators, Dr. Young-John Shin, developed the following theory. I will not go through the theory. I want to tell you about a sort of a neural network. If you have functions which are discontinuous, or solutions of PDEs which are discontinuous, like in hyperbolic conservation laws, then the weights explode. One of the observations you can make is that the weights explode. So the question is, can you come up with a universal approximation theorem when you have a bound on the weights? For example, here we have a bound of 2. We don't want our weights. If you look at the distribution of the weights, and just for those of you, here are the weights. What we are after is these weights, which are basically these lines here and these biases. But these weights, we don't really want these weights and the bias to be greater than 2. So we want to contain the growth of the weights, given some initialization. So there's some details here, which I will skip. But you can see here in this box, what I mean is that we can dial in using the theory. And I want to make the point that the theory is a very practical tool in this case. And I'm after very practical tools. So the theory can lead us to an architecture. And so I just want to demonstrate this here. Given some inputs, for example, in this theorem, like the input dimension, how many discontinuities you have, and controlling the accuracy to numbers that control the accuracy that you want, and so on, how you represent it, some other constants, you can come up with an architecture. Like, for example, I want to approximate not just this function, but actually the advection. So the linear advection of this function is du dt plus du dx equals 0. This is the initial condition, and I want to approximate this. I will tell you how later. But you can see I have an architecture that has 2 inputs, and then the first layer is 20, second layer 26 neurons, 314. Sort of a crazy numbering of neurons per layer that this theory gives us. But notice the results for long time integration. There's this adaptive way of approximating functions, in this case, a solution of a linear advection equation, which is, of course, a deceptively simple equation because we see no dispersion, no diffusion in this, with this simple architecture. Of course, if you dial in any architecture, you get wiggles, you get all the Gibbs stuff and so on, but this architecture gives you something good. So there is some value, there's a lot of value actually in controlling the weights, not just computing the weights, but controlling the weights and connect that to the functions that you're targeting. As I said here, you sort of dial in some of the properties that you're targeting, like the number of discontinuities. But the main thing I want to talk about today is data, how to combine data and PDEs in a seamless way. And I work a lot with the Department of Defense, and somebody from the Army gave me this 5D law that the data, he said, their data is not smooth and nice like the academic people like. They're dinky, which means small, dirty, noisy, dynamic, streaming, and deceptive, they said, because there are Russians everywhere. Sorry about that. I don't mean to offend anybody, but I wanted to quote this anonymous army person. So if you have this data, how can you use them in the together with PDEs? Of course, there are lots of the data assimilation methods and so on, but we know how expensive are current data assimilation methods. So from the three scenarios where we are used to for a long time, I work on lots of different methods myself, and I always look at this left scenario where I know the physics. In other words, I know the PD and I know the parameters, all the parameters of PDEs, and I know the smoothness. And then I have small data. Presumably, this will be my initial and boundary conditions fully determined. But more often than not, I don't know my initial conditions and boundary conditions. I don't know these small parameters in front of the important terms. Even the Reynolds number in Navier-Stokes, I may not know. There are other many properties in multiphysics problems, especially constitutive laws, dirty plasmas, and so on. Partially ionized plasmas. There's lots of uncertainty. How do you take that into account? How you use data to improvise. So I'm looking at this, today I will be looking at this middle scenario where I know some of the physics and I don't know some other part of the physics, or I may not be able to resolve it. For example, in turbulence, even in isothermal turbulence, I know exactly the equations. We know they're valid. However, if it's high Reynolds number turbulence, there's no way, even with exaflop computers, I can resolve geophysical turbulence at the scale of 1 million or hundreds of millions in terms of Reynolds number. Okay, so there's no physics scenario. I will skip it today, but there's also possible to do something on that using lots of data and discovering new equations or new operators. In fact, I'll talk about that later. So I think this brings me to PINs, physics-informed neural networks, which I already defined. As any new idea, this idea was resisted. It took us 2 years actually to get this paper published because nobody wanted to use it to publish the paper. And now this paper has already, I think, in a year, it has more than 700, close to 700 citations. And it's a very simple concept. Let me introduce the concept of a pin. It's, as I said, this is a neural network, like we said before. Here we have 2 layers. Sigma is the activation function. Xt is the input, U is the output. Of course, if I have lots of data, I can learn this very, very well. I can learn this function. No problem, and neural networks are extremely well in approximating this function, continuous functions, and discontinuous functions, as I said. However, I don't have data. In science, we never have enough data. In biomedicine, we never have enough data. But we know that U satisfies some conservation law. Here, I pretend that conservation law is this parameterized nonlinear Schrödinger equation. It could be in the Navier-Stokes. It could be a multi-physics system. It could be some equations and some constraints, anything. One of the difficulties, of course, is how are you going to go back to standard numerical schemes, use finite elements and so on, finite difference spectral elements that I like. But if you do that, then you will end up having a grid. A grid is fine if you are academic and you do homework problems, but if you're in an industry, generating a mesh may take 6 months, a real mesh for an airplane or a gearbox or digital twin of a complex system. So here, instead of using this conventional methods, instead we use automatic differentiation. Automatic differentiation is the same method that allows you to backpropagate the error and in the standard neural network. In TensorFlow, in PyTorch, in all these frameworks now is standard. So we use automatic differentiation, works really well, and maybe not so well for very high order derivatives, but certainly works well. We have to basically take the derivative of the neural network itself. Now, I don't have a network here because if I take the derivatives, this becomes a very complicated network. So what you see here in the box is actually another graph, another network, which becomes very complicated. If you use TensorBoard, for example, you can visualize it, but it's very complicated. It's a nested graph. And of course, if you take second derivative, every time you take a derivative, the depth of this original network, if it's 10, it doubles to 20. If I take a second derivative, I will have a really deep network with 40 hidden layers. So in the process, what you have is 2 loss functions. One will be with a mismatch of the data. The data doesn't have to be at the boundary. It doesn't have to be boundary conditions or initial conditions. It could be anything for initial value, boundary value problem. And then you have this extra term which will help you. It's like supervised learning. That's like the residual that you try to compute at random points inside the domain. I will explain this, but let me just say that despite the complex way of describing this, sorry about this, despite my complex way of describing it, it's a very simple concept, a very simple implementation, and the industry loves it because of its simplicity. So companies like NVIDIA, ANSYS, and Siemens now already started using this. In fact, NVIDIA has already a code, a parallel code that they give for free. It's pretty good code with almost perfect parallel efficiency on their GPUs and so on. So the industry likes it, and also the academic people like it now. And the reason the academic people like it is because they say it's not good enough, so they want to improve it. In fact, recently someone, a student of a friend of mine, gave a talk to my group and said that they improved it by 11,000 times. And I wasn't offended. I was very happy to see all these people having a job and writing good papers. So anyway, let me just explain the concept here using this Berger equation, with viscous Berger's equation. So just to implement, first the setup, the domain is the time domain and the X domain, the space domain. We never discretize these variables. These are continuous variables, xt, and we take automatic differentiation. Here's the star points at the data points, the initial conditions. Here are the boundary conditions, and you can see that on purpose, I don't have a lot of boundary data. I have some boundary data, and that will be my first term in my loss function. Now, the second term is the residual, f, the residual of this Berger's equation, and I need to evaluate it at random points inside the domain, using, like, let's say, a space filling curve or Latin hypercube or some important sampling for high dimensional PDEs. But random points inside your domain, the XT domain, you can evaluate this in NF points. So in terms of implementation and a code, in terms of flow, you define the neural network, which I had here on the left, this one here. It's just one line to define it. And then you need basically to work on the right-hand side. And the right-hand side is only 3-4 lines, transfer the neural network, take the derivative first of the neural network in space-time twice, sum them up, put it in a loss function, then call your favorite Adam or otherwise minimizer. So by doing so, that you can see that within an hour, a graduate student, and even a professor, I joke these days that even professors now can implement their own ideas. And you can get solutions, pretty good looking solutions of Berger's equation in an hour, starting from scratch, not knowing anything about numerical methods. So that's the convenient part I talked about. Of course, there's a lot of danger with that because the solutions, the optimizer will not give you a unique solution. There's lots of dangers. That's why I think there's a lot of room for improvement. I want to show you this. I don't know. Let me ask my chair, Sid. Can you hear me, please?
Yes, I can hear you very well.
And you have not seen this picture before, right?
I don't think so. So I'm
okay. So this is another extension of PIN. We call it the generalized domain decomposition. It's a space-time domain decomposition. So here we have two neural networks. One is the blue sea where the dolphin swims, and the other one is the dolphin itself. It's an arbitrary. It's a gimmick to show you that we can decompose the domain into two subdomains. The blue domain is one neural network. We call it neural network 1. The dolphin domain is another neural network. So we can decompose space-time. We can simultaneously work on both domains. So I will speed up the operation by a factor of 2. If I do it in 100 pieces, I speed up the operation by almost 100 because I can get almost parallel speed up. And the reason I get parallel speed up is unlike these continuous Galerkin methods where I have to compute fluxes and continuous Galerkins, dealing with stiffness matrices and so on. Here, the extension is very, very simple. Basically, we want to simply make the residual of the conservation law continuous. So that's very easy. So you can have convex, non-convex surfaces and so on. And you stitch these solutions together very simply by penalizing the jumps of the residual, which of course is zero. You have to make it continuous. In the process, we create a parallelism, of course, as I said, but also we create great flexibility. For example, here I can have a different neural network on the blue sea, and I can have a different neural network on the dolphin. I can use different activation functions and so on. And down here, you can see that because I control the number of points on the boundary, I can have a really seamless integration in space-time. That's what I want to make the point, that I have parallelism in time, which, as you can appreciate, for initial value problems is not trivial at all. You can use parareal, but there are other problems where that's not so easy, especially hyperbolic problems, to do that. Okay, so that's the one extension. I will talk about that later. This summarizes this generalized domain decomposition. Again, if you have an arbitrary domain like this, you can have multiple subdomains, and then each subdomain. This is especially good for multi-physics, multi-scale problems, where you have boundary layer, you have multi-rate, for example. If you have chemistry, later on I will show you what happens if I have chemistry with hypersonic problems, very difficult problems, but this gives you an extra flexibility for it. Let me show you a couple of applications. This is something we published in Science last February. We call it hidden fluid mechanics because we pretend that we have data, not only their noisy data, but their data on an auxiliary field. I don't have any data on the velocity and the pressure. I'm interested in the velocity and the pressure in fluid mechanics, of course. I have data on a passive scalar. For example, if you follow clouds, if you have smoke, I have data on the smoke. I have data on the dye, something that to visualize what's going on behind an object. Like here, I visualize a patch of my domain of interest that is this patch, and I have a video of that. Okay, can you use this video to extract the velocity and pressure there? So as long as you have some gradients of the dye, like I have here, and some time snapshots, then you can compose a neural network, which is this multi-physics problem, namely the passive scalar and the Navier-Stokes equations with incompressibility constraints. Very easy to, in this framework, with like Lagrangian multipliers to include any type of constraints. But basically, using the data, the auxiliary data, then you go to primary data. That's why we call this hidden fluid mechanics, because it's sort of an analog. It's not exactly, but it's sort of an analog of a hidden Markov process. You know, auxiliary data, you're trying to infer the primary state. And that's what we do here, down here for one snapshot for the velocity and the temperature. The inferred dynamics is within 1 to 2% what you would get if you knew everything and if you were solving the forward problem. Of course, here we solve the inverse problem together with the physics. If you have this dye going around the object, you can see I can even compute the forces on the object, which is something useful if you do experiments in a wind tunnel or a water tunnel, and do that. Now, this is another ill-posed problem, timely. We got this from a YouTube video. We downloaded, that's how we became friends with LaVision, a German company, big company on lasers and visualization. So we said, okay, can you estimate, can we actually infer the velocity field around the mouth and the nose of this person? This is actually our collaborators, Thomas Berg and LaVision. And when he wears a mask or without a mask. And here I just show you that we can quantify totally in time, space, the pressure field. This is a pressure puff that comes out of his mouth. We can quantify it. If he wears a mask, there's very little pressure field. You can see highly reduced. There's a little bit from the side because he didn't use his mask very accurately, but basically the velocity field, which we also computed, is 10 times smaller with a mask. This is another. I'm not going to show you a lot of applications today. I like applications, but I just want to make the point. Working with real data, this is ultrasound testing of materials from Wright-Patterson Air Force Base. They use that technique for the wings of airplanes and composites. This is an aluminum alloy. There's a surface crack. You can see that you put an ultrasound module here, and you send them ultrasound. There's a surface crack, or it will reflect the ultrasound, and from that you can see where the crack is. How you quantify exactly the crack is we use physics-informed neural network here by having the wave equation in the simple problem. You can use the full elasticity equations if it's an immersive crack. But in this case, This was a hackathon by a dozen teams in last year in DARPA. There was 12 teams, as I said. None of the teams were able to do it because they said they didn't have enough data. We found we had too much data. We only used 10% of the data, of the ultrasound data, and we nailed this problem because we were able to actually quantify the wave speed, as you can see up here on the right. And if you quantify the wave speed, then you can exactly determine where the crack is, the size of the crack, the orientation, and everything, okay? Now, the key to this was, of course, to include physics, and by including the physics, you don't need so much data. You also have noise, and it regularizes the problem instead of using the arbitrary weight regularization using neural networks. So, but another important development was that we use what we call adaptive activation functions, and I want to show you what this is. We had done a lot of work in the last 3 years on this adaptive activation function. So, as you know, in neural networks, we have one non-linear activation function, which I called sigma before, and that is the same for all neural networks. However, there's no reason for all neurons to fire at the same rate. There's no reason why all layers fire at the same rate. So we can make the activation functions layer specific, or we can make it neuron specific. And we can introduce a parameter for each one here, A, and here you see I parameterize different activation functions to show you that every neuron could have its own mind when to fire. Now this A becomes also a hyperparameter, so now my trainable parameters using the stochastic gradient descent will include the weights, the bias, and new parameters. These are not that many parameters, so even if every neuron has its own firing rate, it's a small problem compared to the weights, for example, where you have all these combinations. But you can do a layer-wise, so that's actually, it adds maybe 10, 20, 50 parameters at most. So in fact, we found from practice that the layer-wise activation, adaptive activation is even better. This factor N here is a factor that the user can use to be more aggressive or less aggressive on this. Just an example here to see how this, let's say we try to learn this function. And if you use adaptive activation function, after a few iterations, you can nail the function. In fact, you can recover its Fourier spectrum here on the right totally for this low, high frequency, even discontinuity. It generates a long tail spectrum. You can totally recover it with adaptive activation function. With a fixed activation function, you can see what happens. You get stuck into a minimum and you're there. But this is a loss, but you can see that eventually with the adaptive activation function, you can get the loss to a small value. We have used that for benchmarks like NIST, CIFAR, and so on, and we beat everyone. So is there a theory behind it? There's actually theory. One of my postdocs, Jagdap, and Ameya Jagdap and Kenzie Kawaguchi from MIT CSAIL, they prove a theorem that shows that adaptive activation functions, depending on the specific case, eliminate BAT minima, which is a big deal, of course, for training. So it's very useful, especially if you have noisy, if you have rough landscapes and so on. This is very important. There's another part of the theorem, I don't have it here, that shows that effectively what you do with neuron-wise activation function is like you have a second order SGD without paying the price for Hessian. So as you know, people like Jordan and so on have done a great job in high order methods, except nobody's using them in practice because they're very, very expensive if you have to compute Hessians and so on. So you can use it at sort of later stages, but this one allows you from the very beginning to go to high order. Okay, I want to kind of summarize what I said here. We develop lots of different methods. By now, but I haven't show you anything, just standard pins and X pins. There are pins for high speed flows where we can bring conservativity, the variational pins, stochastic pins, and blah, 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 blah. But here it's a stochastic pins. We use GANs. If you don't know GANs, GANs is a really great concept. It's this adversarial training of of a generator that uses arbitrary noise as an input. It generates fake data. The discriminator, which is the target network that you want to train, sees both generate data and real data. We have shown in this paper in CISC, which again took 3 years to publish this paper because people don't like to see new things. We realize that we can actually dial in any stochastic process. If you can dial in stochastic processes, you can definitely do stochastic PDEs. This is an example of a PDE that we solve, a stochastic PDE. It's the problem setup is such that I know something about the right-hand side, which is stochastic excitation. I know a little bit about the solution, some measurement somewhere, and we know something about the hydraulic conductivity. We apply this to real problems like this Hanford site, which is the largest nuclear waste site in Hanford, close to in Seattle, northwest of the United States, where PNNL is, where I'm directing the center. We had an application. So this is kind of introducing uncertainty in a stochastic PDE. Now we modify the standard GAN to have also a generator for all the stochastic fields, the right-hand side, and maybe the boundary conditions, generator for the conductivity and U. So then the discriminators see this concatenated vector of realizations from the stochastic fields, plus some real data. This would be real measurements, for example. If you're looking at porous media, there will be like 1,000 wells, which there are data actually from this huge nuclear waste site and so on. So what was the benefit from this? I will not go through all this paper, but we were able to go to 120 dimensions and eventually 10,000 dimensions using a big computer. But we didn't quite beat the curse of dimensionality. A lot of people talk about that. But we made the cost almost linear, quadratic at most, with a number of dimensions. Variational pins has a nice mathematical underpinning to it. It's a, let's say you're trying to solve this Laplacian or Poisson equation. You can integrate by parts once or twice, and you can mix spaces. One of the interesting things with if you use a Petrov-Galerkin approach, you can have the neural network being the approximation space, and there's a good reason for that. I show you this adaptivity built in that nonlinear space, and then you can have the test functions being smooth functions. There's an elegant way of doing this. In fact, with simple Relu and Stein functions, you can find.
George,
yes. Yes.
There are questions that are coming in, but my suggestion is that we take all the questions at the end. Is that okay for you?
Yes, because I want to show you the DeepONet, and yes. I cannot afford to
yes, exactly, right. So let's.
So this is to show you here that. Thank you, Sid. This is to show you that actually you can write analytically and do some theory. You can actually, with a ReLU function, you can write analytically also for a couple of more layers, and because you appreciate if actually how this. In these mixed spaces, how these residuals look and how these are different methods and so on. So variational pins is interesting. Let me briefly talk about the math of pins. This is a big frontier. This is, I think this audience would be really interested in that. There is this approximation, especially, I will not talk about here, but approximation when you have this, 5D data I said earlier, the multi-fidelity data, not all data are the same level, and how you bring that in. The nonlinear approximation theory. But the main issue here is generalization. And I want to mention the two seminal papers by the chair, Sid Mishra, who was motivated by some of these applications of pins and produced perhaps the best two papers on generalization already of pins. Now, generalization error refers to the fact that although you're in this neural network, this HM space, and you can do a good job from the approximation, the universal theorems of approximation, you can minimize this by making a really big and expressive neural network, making this box bigger and bigger, going closer to the true solution. Then there's always this generalization error because you replace you can never exhaust the training space. You have to use you go from a integral to a quadrature, so that's very important error. Of course, there's always the optimization error, the fact that which is another beast, but you can see now how this analysis of these approximations for PDEs is much more, even for functional approximation, but certainly for PDEs is much more complicated. The other complication is that I'm interested in solving ill-posed problems. So you don't have the standard well-posedness. You have to find conditions or for conditional well-posedness. And that's the paper of Professor Misra that they exploit that type of knowledge. And another paper that some of my collaborators worked on is based on a different approach to this, again, tackling the issue of convergence generalization, but for linear PDEs and elliptic and parabolics. First of all, we wanted to show that even without the boundary conditions, pins converge as you make the space HM bigger. It converges in the L2 space. If you include also the boundary conditions, you can find the H1 converges. Another paper, which we haven't put on the archive yet, but it's complete, we're just about to submit it, is using equivalence of norms and compactness arguments to derive a priori and a posteriori error estimates in terms of either the solution or actually in terms of the functional, which you compute at the a posteriori. And there are two formulations, the discrete formulation and the continuous formulation. And this down here is a sketch, just standard. When you have a continuous formulation, if you have the expressivity of the neural network, you can show convergence. The generalization, we refer to generalization as compatibility, compatible neural networks, or other conditions. I don't have time to go through this. It's a very technical paper, but it will appear in the archive soon. Sid, I don't know if you can see this movie. It's a huge movie, so I don't know if you can see.
I can see it perfectly.
A destroyer, a real destroyer of the US Navy going through North Atlantic. It's supposed to be autonomous, no crew, no captain. Can we do it? The answer, we cannot do it, because if I were to use CFD to predict how the dynamic motion of this destroyer, it takes about 1 week for one simulation for one state. This is sea state 8, where 20 meters waves are in front of you. This is a real spectrum of the North Atlantic. So standard conventional methods will never meet what you need for autonomy, for cars or airplanes and so on, or the ships. So we want to use neural networks to approximate, as an input, we'll have the stochastic input as the stochastic sea elevation. As an output, I will have the sea keeping motion, the dynamic degrees of freedom. So that gives me the opportunity to talk about the second theorem. That second theorem is by Chen and Chen. And it just so happened that Tianping Chen, who developed this at the same time as George Saipengo, he's now 87 years old, and he sent me an email this morning.
What a coincidence.
Yes, and he proved this theorem. I mean, it's such a, not many people know about this theorem. He proved this theorem, and he published in IEEE Journal in 1993. So he says, yes, there is a network that can approximate that. How can you do it? It turns out, with today's technology, we can use an LSTM, we can use Google's sequence to sequence and so on to have a stochastic input, 2 different realizations to get like 3 degrees of freedom. And you can see here, this is now the first column is for the first excitation, second column is second excitation. This is all unseen data for the trained neural network that we can predict the functional. We can predict whatever you want. You can predict the time series here. Underneath, you can see the CFD in red, but clearly we can do a very good job and how fast you can do this? You can do this in 0.01 second on a laptop. So now we are meeting real-time requirements. That is interesting. More interesting, and again, going back to Chen and Chen, at the same time, a couple of years later, they proved something so profound, which these days I spend all my time working on this topic. And that is, if you really want to talk about generalization, you have to go to higher levels of abstraction. Over-parameterized neural networks may do a good job, and there's a lot of controversy and lots of interest in that. But if you go to a higher level of abstraction, if you learn that operator, you know you can do much better. You don't want this robot here to go through all the calculus that we did, because then they have to calculate the way we're trying to calculate using hexaflop computers. So this robot will have a huge head, an exaflop computer with a thermal cooling system, which is bigger than my house. So that's not the way to go about intelligence, collective intelligence, and so on, robots. The way to do it is by system identification, by offline training, and so on. So this theorem of Chen and Chen basically extends the Saipenko theorem and their own theorem to nonlinear operators. So now the input is functions from this space, compact space V. The output are functions, and G is the mapping of the input to the output, is a nonlinear continuous operator. So the theorem of Chen and Chen says that any mapping like that, any nonlinear operator, use the input, can be approximated by this double summation on a neural network, which is the output here, which we'll call trunk, and an input, which we'll call the branch. So you can see the input is here, which you sample from the space V, and then the output is there because that's also the output itself is because you have now G of U of Y is also a neural network. This is for a single layer, but recently, and this is in the paper that is coming up in Nature Machine Intelligence, we proved that this could be also extended to an arbitrary deep neural network. It's not very different from there's some technical arguments. The compact space, of course, in application, the compact space is a big constraint, but as you will see, most of my examples, I take a compact space, which is a Gauss random field, which is not non-compact. So it works with non-compact, but it's impossible to prove it. Okay, so what is the setup? The setup is here. Let's look at panel B. I have panel B. I observe my function U, a second function U, another 100 different functions U, and then I observe the output at a few points. Usually observe the input at many more points than the outputs. If I go back here to panel A, then you give me a new function from inside or outside the space V, and I want to give you the output in terms of functions, okay? Now, one of the main things when you have the approximation theorem is, as I said, generalization. We talk about generalization. The question is, can you design neural networks with small generalization error? And today, there's so many papers out there, one can try everything. The space V, by the way, is very important, as you can appreciate. So that's also an area of where research can go. I just want to give you a teaser. If we use a Gauss random field here, is a Gaussian, for example, with a kernel with a correlation length L, and if I do a sampling with uniform sampling, you can define this kappa here in terms of M, the number of points you're sampling in the space V. And then you can find that kappa is of the order of M squared, 1 over M squared, number of points square, you sample in correlation length square. And then you can prove something like that this neural network that approximates this operator G is certainly bounded by this error, okay? Now, how you materialize this, how do you actually implement this in practice? This is our contribution. We propose this neural network. Let's consider this unstacked case, which turns out to be the best in terms of generalization error. So there's the branch network that implements these big parentheses that will relate to the input. And then there's a trunk, the output. And then here you can see we just do this math here by crossing it on P points. P are the points on the output. K defines the output. M is the number where I'm sampling. Okay, so DeepONet, this DeepONet is based on rigorous approximation theory. I want to give you a very simple example how we actually do this. I'll be done in about 8 minutes. Is that okay?
Absolutely, George. Take your time.
Okay. So this is an integral. You can see that I use 10,000 functions. I only observe at one point, and I find that I can learn this integral operator. And here the testing error and the training error is basically about the same. If you use another full feed-forward network or something else, you can see this difference is the generalization error. So I can learn these functions. I can learn exponentially fast. This is a pendulum. The input is U, the output is 2 functions. You can see that I can learn exponentially fast for this network, but then eventually I saturate to algebraic and very slow convergence. I guess somebody out there, maybe in the audience today, is smart enough, smarter than us, to design a neural network that will maintain this exponential learning rate. You can do that for PDEs. I want to show you that I can do it also for fractional differential operators. And here I use a Caputo derivative. A Caputo derivative, let me just show you what it is. A Caputo derivative is defined up here. The singular kernel used in initial value problems for fractional PDEs. So the idea is again, I use standard numerical methods to derive these outputs. I use lots of functions as an input, and then I can, it's expensive to evaluate. Everything in fractional is expensive. So can I amortize all that cost? Can I learn DeepONet that does that for me? It turns out yes. And this middle plot here is to tell you that the mean square error can be very small, but it depends so much how you actually approximate the input space. For example, if I use a GRF, I get this green line. However, if I use polyfractonomials, which is a spectral methods that I extended to, like Lejeune polynomials that I extended to fractional singular value problems, then these are eigenfunctions of those. If I represent my function V, I can increase the accuracy tremendously, and then I can compute these fractional operators. I can infer them very quickly. This becomes very important for the Laplacian in bounded domains. Here my space V is represented by Zernike polynomials. I don't need a lot, but you can see again, if I use, in fact, one can use other neural networks, CNN. This is one of the cases we found in a nice domain like this, that the CNN, I can map this to a nice image square. It could outperform actually DeepONet. So DeepONet is very powerful, but it's not necessarily the best. And I'm sure the concept is very strong. Other people can find. I'll skip the stochastic differential equations because it's very similar. For example, with color noise, you can see what we're doing here. The input is represented by Carhoeven-Loew expansion. So the input is bigger and the output is, of course, space becomes bigger. Using this truncation, I get very accurate solutions for samples. I want to show you this. This is DeepONet now learning Euler equations with non-equilibrium chemistry. Okay, this is not a trivial, even for WENO. This is a recent paper that my colleague Xu produced in JCP. He gave us the code to generate data. He gave us the code. You can see we have 3 species. We generate this data. We only took 100 trajectories for training, and we used 50 trajectories for testing. Now, here's what we did. We used the conservation laws. We started from initial conditions from nitrogen, oxygen, and velocities, and so on. We can basically predict at any time, and in xt, we can predict all this. And we can predict it very, very quickly. What the input is this parameterized form of the jump in the pressure and the smoothness of the jump. Of course, from that, you can generate a lot of initial conditions. So eta is very continuously between 0.02 and 0.2, and basically you're controlling the gradient of this and the jumps in the left and right in this Riemann solver for initial conditions. So that can give you anything. But here's an example. After some time, I can predict, for example, at targeted time, this red line started from initial conditions from black. You can see for all species, I can predict, again, without solving the problem. The DeepONet can predict this with 10 to the minus 5 accuracy. We have some theory for it. Let me give you a teaser for conservation laws. This is the theorem that shows error estimates. On the right-hand side here, I have the number of points where we sample the input. Here, P is the output, 1 over P. Then here's the parameters of the branch network. And this at NT is the number of the trunk, which is the output network. This looks good, except this middle term, because here I have square root of the number of points. And this number of points is a large number. So we're trying to get rid of this to something, a log or something like that, but to prove convergence. So So this is an open problem. I invite you to actually do theory better than us. We are still working on it ourselves, but if you have any ideas, this is a good place to tackle. Let's see how much time do I have. Let me take 2 minutes to show you this hypersonic problem because I want to talk about DeepONet, DeepMNM. So DeepONets are building blocks for very complicated problems. So this is a current problem of interest around the world, from the Chinese to Russians, and especially the United States. So I'm looking here at a specific example of 5 species now, non-equilibrium chemistry, Mach number 8 to 10. So I use standard solvers to learn DeepONets for all these fields, separate fields. Okay, I use 240 trajectories. I use a DNS to produce the fields in this Mach number 8 to 10. You can see I can go from chemistry to velocity, and temperature, from temperature to velocity. So these are my data sets in this Mach number. I want to show you that it's not trivial. Look at the velocity. There's a very, very steep structure, both in the species and almost 8 orders of magnitude. So here we do Mach number 8 and 10. Then we can predict from temperature and velocity, we can predict all the chemistry in 0.01 second, and vice versa. But the concept of MNM is the following, is multiphysics, and basically in hypersonic problems and other electroconvection and so on, you have some measurements somewhere, for example, for the slow scales. For chemistry, you may not have anything except the initial conditions. But here, on the fly, literally, you may have some measurements for velocity and temperature and pressure, for example. So you use this, you have these prefabricated, pre-trained networks offline. In a split of a second, you predict the new fields. Then you pipe that through these other DeepONets, which are pre-trained. And then with this loop, this is a standard neural network, you now have a loss function which you test your operators. This is the operator here. Basically, why are the fields you're trying to predict versus the outputs of the operators. And then these are the real data. And we have shown that with just very few data, 2-3 data, you can really solve multiphysics problems for unseen data. And this is a paradigm. We have not published this yet. This is the first time, actually the second time I show this. I showed this on Friday. But this shows you the possibilities that, so in terms of accuracy, the accuracy is pretty good. In terms of speed, we do 50,000 times faster than DNS in predicting this. Let me finish here. I want to treat you with my espresso coffee. Now you can see the mug has the same thing as my background. That's a DeepONet. No, DeepONet, that's a pin. And I want to tell you a story about this because LaVision, they give us this data and we predict that the maximum velocity in my espresso cup is 0.4 meters per second. I said, I'm an engineer. I know about these things. There's no way that this is 0.4 meters per second. It's such a slow flow. And then they said, yes, they only find 0.08 meters per second from their naked eye type of measurement. Then they set up an experiment with PIV, particle image velocimetry, and they found that indeed the velocity that the neural network predicted was 0.4 to 0.45. So it was a blind comparison with it. We're very gratified to see this. And there's a library for those of you who want to start playing with this. For any DeepXD, works for any, at the level of education, not at the level of real problems, but it's a good way to get started. This library, I was just told by my collaborator, has 56,000 downloads. And it's about a year old. So I guess students are using it a lot. I would like to thank Springer, and I'd like to thank Sid for inviting me here today. And I don't know if there's time, I can take some questions.
Yes, absolutely. First of all, thank you, George, for this superb talk. Really a tour de force, if I may say so, with lots of different concepts, as we expect from you. So we are delighted that you gave this talk, and it has a lot of response. There were already a lot of questions. Of course, we all are busy people, so I try to ask you some relevant ones. I have the questions in front of me. Someone is saying, for instance, this one is a relevant question from Nick. does the work on STEs with PI GANs work for etostochastic PDEs as well?
Really good question. I was asked it before. We don't have that yet. There is something we published. In fact, yesterday, every Saturday at 11, we have an ad hoc group working on something like that. But we have something that you may be interested in. It's called generative ensemble regression. So we're looking at from unpaired data. We're looking at stochastic ODEs and so on. But we are considering this, but we don't have anything that we can answer this meaningfully for you. So most of the stochastic stuff we did so far is more like color noise with truncated and so on, not what you have in mind.
Someone is asking about Caputo fractional derivative. Maybe I just built up a little bit on this question and ask you this work on fractional, you had this enormous body of work on fractional derivatives before, and now with this F-pins. So what's the message here? Means, is it that there are certain models where fractional derivatives are good, or
So
you are sort of quick through that, right?
No, you're right. So the main idea is to cut the cost. Of course, with fractional pins, and that will, that's a good question because I need to clarify. There's no automatic integration in any of these frameworks. There are automatic differentiation. Automatic integration is basically what I show you, that 1D. We're trying to use DeepONet. So I was thinking how we can build basically automatic integration using this DeepONet. And of course, if you do that, then you can deal with integral operators, Caputo or otherwise. In particular, computing the fractional Laplacian on a finite domain is really very expensive. And I have written papers on H-metrics, and other people have done that, and so on. But still, we want to compute, and this comes from a real need. For example, I was trying to do turbulence simulation subgrid, and I wanted to use non-local models for that, and it was almost impossible. Although it was more accurate, it was very expensive to compute non-local subgrid models for closure. So we thought that we need to do something like that to compute, fractional Laplacians and gradients and so on, to compute it pre-compute it and just spit it out very quickly. That was sort of the motivation.
I see. But maybe I ask you a question, just a quick follow-up on that, because you have this very nice machinery of DeepONet, which I have to understand. Each time you give a talk, and I feel that, I have to understand this more. Now, so now you had this compactness assumption somewhere in the approximation, but you have been
on the input space, yeah.
The input space, but you've been using sort of Gaussian random fields and fractonomials and so on, where this assumption is failing, right? And at the same time, getting excellent results. So
yes. So I think you will see also in the Chen and Chen, if you go through the theorem, you will see you need that to do it. Now, if anybody wants, if you're able to, like with some weighted space to remove that and go to infinity, but weighted, I think that's probably. I mean, but we haven't been able to do it. So, but you're right. For example, you want to learn Laplace transform, right? To do quickly Laplace transforms from arbitrary functions and so on. That's very important. And so that's why we are pushing this for the applications, but the theory itself doesn't cover us for that case.
No, but of course, theory is always late to the late to the party, right? But another question
but it's very important. I mean, that if we can even not totally remove, but like use some weighting, weighted spaces I think that will be a huge step forward also.
And what did you use for the input space, for instance, for this compressible Euler chemistry problems? What was was it a finite dimensional input space that you used?
Yeah, that was a finite dimensional space. And one of the questions that we asked, and kind of really interesting question, is what happens if you extrapolate outside the Mach number 8 to 10, let's say, you go to Mach number 13. It turns out, actually, that's what DARPA is interested, of course, and it turns out it works really, really well. For example, in the worst case scenario, we get a DeepONet to give you 20% error, okay, without nothing. Now, if you increase the number, if you enrich that space V, like I use only 100 trajectories. If I use 300 trajectories, the error, the extrapolation error, that's the interesting thing. The extrapolation error goes down to 10%. So you refine more the space, the input space, then you do a better extrapolation, which makes some sense, but it's good to see. That may depend on this on the application also. For example, if I go on the other side, on Mach number 7 or 5 or 4, because there's no chemistry, I cannot predict it very accurately.
No, of course.
So it depends also on how smooth the solution extends to those, those things. But it's really interesting from the point of view of the application, as you can imagine.
Absolutely. Yes. So any further questions? If not, I think we stop here. We all have to go, and we thank, no, there is one question. Yeah. So it's for next week. Yeah. Thanks a lot, George, again, for this very sort of, as I said, it was a real tour de force with so many different components, and one really has to think a lot in order to just get things absorbed. So thank you very much. And I think it's highly appreciated what you're doing. Ciao.
Thank you. Thank you, Sid. Thank you very much. Thanks, everybody. Have a good day.
Ciao, George.
Bye-bye. Ciao.
Thanks a lot. Thanks for joining, everybody.